Check. Good evening, everybody. Thank you so much for joining us here at Great Basin National Park for our 14th Annual Astronomy Festival. Thank you so much. It's only because all of you show up every year that we're able to do this. So thank you for giving us the best jobs in the world. So this year, our guest speaker is the illustrious Dr. Plotkin. He comes all the way from the University of Nevada, Reno. He is one of the researchers that works on our Great Basin Observatory. The Great Basin Observatory is the only research-grade observatory inside a national park. We actually celebrated its 7th year of operation this year. So it was built in 2016, completely from donations from the Great Basin National Park Foundation, who fundraised in order for us to build it. So it's a really remarkable thing, incredibly unique to our park, and we are very lucky to have it and have excellent folks like Rich who get to work on it and do some real science. So he's going to tell you all about some of the research and things that go on with it and how special it is that we get to bring it to all sorts of people that you wouldn't necessarily think of as traditional astronomers and researchers. So I'll pass it over to you, Rich. Thank you again all for coming and enjoy the talk.
Talking more a bit more. All right. Well, thank you all for coming. And my slides are designed for darkness, but that shouldn't be a problem in about a half hour, I hope. But I was asked to come tell you about some of the fun we've been having with this telescope. It's really a pretty amazing resource that we have in order to, be able to study the universe from this place, which is incredible. If you bear with me for a second, I'm going to move this to the other side, so when I look that way, you can still hear me. All right, still working? That's better. All right, so a little bit about me first. My research is focused around black holes, so I spend my days basically watching black holes eat. We see lots of different kinds of black holes in the universe. This is a picture of a black hole that, probably too dark for this right now, but at the very center where the blue part is, that used to be a very, very massive star, probably 50, 60, 70 times more massive than our sun. It went supernova, left behind a black hole, this compact point that nothing can escape from, not even light. And this system happens to be in a binary. This is an artist's drawing. This isn't a real picture, by the way. It's in a binary system, and there's another star that's donating material from its outer atmosphere, forming an accretion disk feeding the black hole. And so most of my work is pointing different types of telescopes. I use a lot of X-ray telescopes which fly on satellites run by NASA, and I use a lot of radio telescopes, mostly from the National Science Foundation, to basically watch black holes like this eat. As stuff falls in, it releases a lot of X-rays. Stuff gets really hot, shines really brightly, and sometimes some of the material falls into the black hole. Some of the material actually gets shot away, and that's what those two kind of perpendicular parts are trying to show, are these relativistic jets that are shooting away from the black hole. And these shine really bright radio waves. So if our eyes could see radio, if our eyes could see X-rays, we would see these types of things. But for our lives, we need to basically use different types of telescopes to be able to see them. And so most of my work is focused around these types of things. We see this type of system in our own galaxy. The closest one is about 3,000 light years away. The farthest one that we know of is, maybe about 50,000, 60,000 light years away. But very similar types of things live at the very centers of galaxies. It's these supermassive black holes that live at the center of every single large galaxy. And I also study those when they're shining very brightly, shining as quasars and active nuclei. So that's what pays my salary for the most part, and teaching at University of Nevada, Reno. Here is the picture of why I'm out here today, because another part of my research will involve the Great Basin Observatory, which hopefully you can see a little bit, but towards the right, there's the dome. That's what houses the telescope. And then there's a kind of a ladder going in so people can get in there. And as Bradley said, this is the first, and I think maybe only, research-grade telescope in a national park. And it's really an amazing, amazing resource that we have. And at University of Nevada, Reno, we basically have free range at it. We can almost point this thing to anywhere we want in the sky at any time. It's 0.7 meters in diameter, so that's the size of the primary mirror. So it's a very, very, I'd say top-of-the-line type of telescope that an amateur might get their hands on. Now, professional astronomers, our biggest telescopes are 10.4 meters. right? So it's not very big compared to what the state of the art is, but this thing has the flexibility that any large telescope will never have. Usually when we try to get time on big telescopes, you write a proposal 6 months to a year ahead of time, you wait a long time, learn if you get the time, or you don't, more likely you don't get the time, and then you submit your observation probably 6 months ahead of time for it to eventually get observed. You really have to do a lot of planning. This, you could just see a supernova go off the night before and just point this thing to it within hours. Like, it's really incredible the amount of flexibility we have. And even better for someone like me who enjoys my sleep, this thing is remote. I don't need to drive out here. It took me 7 hours to get out here today. Worth the drive, absolutely, but I don't want to be doing that every night. I want to observe. We can just go online, go to computer. Anyone in the world can just access a web page if they have the password and put their observations in. And you can do that during the day, anytime. And then when the conditions are right, weather is good, your source is high up in the sky, this thing just opens up, observes, puts the data into a Dropbox folder, and we get it the next morning. So it's extremely convenient, it's extremely flexible. I use this a lot to take nightly observations of the same source to see how things might change with time. I'm monitoring a black hole right now that just went into outburst in our galaxy. And what I'm really going to be focusing a lot of time on, the laser pointer is starting to show up a little bit, is this is an amazing resource to train students, to train the next generation of scientists. You can, this is something you can put your hands on, you can play with it, you can try something, let it fail, try it again, right? When you're using our 10-meter telescopes, you get one shot at it. If it doesn't work, maybe you'll get another chance. This, you can really make your mistakes and really just learn through the practice of actually trying. So this is why I'm involved with the Great Basin Observatory, and this is why I included both in my research and in the courses that I teach at University of Nevada, Reno. By the way, please interrupt me at any point. I love when people ask questions, so I have a bunch of slides. I'm perfectly happy not to get through my slides if this turns into Q&A, so feel free to put your hand up. These are some pictures of the telescope. I was just telling over here, I've never actually seen this with my own eyes. This is only my second time at the park, unfortunately, and I've never been able to get out there and do it. But this is the structure, that's the structure that houses the telescope to the right. Obviously, we keep it covered during the day in a dome, and then at nighttime, the dome opens up and the telescope observes. It's not that big. If you can see the ladder in the back that would climb you into the dome. If you're inside the dome, what I hear is you can't even really stand up in it. You're kind of hunched over like this, someone my size. So, it's kind of just a nice little compact, really efficient system that we have. And then there's the control room over there, which houses the computers that control the telescope. All these pictures were taken by Paul Gardner, who needs a really big shout out. He is the engineer that really got this thing up and running in terms of getting the software up and making sure this thing operates every night. Here's inside the dome. Obviously, there's not lights on when we're actually observing. This is for a photo op, but you can see the dome open, the telescope pointing, and then the beautiful, beautiful sky that it's observing. For those who have their own systems at home, this is our calibration setup, so that's the white screen that we take our flat fields off of and our calibrations. We take calibrations every morning, but they're usually good for about a week or sometimes a month. It's a pretty stable system. And then there's inside of the control room. We have basically 3 different computers. One monitors the weather, one actually controls the telescope. And I don't know what the third one does, but I know there's 3 there. A bunch of storage, climate control, that type of thing. And these computers, we log into them remotely from anywhere. So we can get into the computer and do whatever we need to do. And most stuff can be done just online. Every once in a while, and this is I think where Bradley comes in a lot of times, he needs to go in and push a button to restart the dome or restart the computer and stuff like that. So we do need people around. And the Rangers here have been amazing at helping us keep this thing operating and running every night. But for the most part, we can do most of the science and most of the things that we need to do from the comfort of our home or our office. And it's easy to use. That's my 6-year-old, at the time 4, taking observations. And like she actually, so the laptop there has the, that's the software to control the telescope. And I mean, she actually did this. Maybe I shouldn't tell you, my 6-year-old moved the telescope. I told her what buttons to push and everything, but she was doing it. And then that's her playing with some of the data on the other monitor. So, I mean, the power of it, it's so easy to use once you have the smart engineers setting it up for us. Even people like me can use it. And it's just great this is a case we decided to observe live. And I will actually show the data towards the end of this talk that we took here. And so if you want to do that, it's great. You just log in, go online. There's just a web address you go to and you can observe. But if you don't want to do that, you can preset your observation up. It just goes into a queue, and when the conditions are right, you just get your observations. It just does it for you. So it's right. It's really good for like taking repeat observations of the same source every single night. When unexpected things like supernova go off or outbursting black holes, we can get on them really quickly. And right, I love that I can sleep and still do science in my sleep. Right.
How many observations on a night usually?
It depends. I have done probably at the peak 10 or 12 different sources per night. I will admit I've done 0 sources per night as well. So it just kind of depends what's going on in the universe. But you can take exposures anywhere from 5 seconds up to like 10 minutes. And you can, I have once or twice watched the same source over 6 hours as it rose and set. So, yeah.
Explain observations. You spoke about them almost you're making observations prior to if you were using a telescope. I could understand observations after using a telescope. I'm not sure what you mean by before.
Oh, so when you want to make so instead of actually physically being, so the question is, what does it mean to make an observation before you made the observation, which I probably phrased poorly. So what I mean by that, instead of actually going there and telling the telescope in real time to slew to this part of the sky, and then telling it in real time, take an exposure on our CCD camera for 5 minutes, and then doing it, you make a plan. You say, I know that I want to observe some star that has this coordinates in the sky. I know I want an exposure in whatever filter for this long. And so it's basically like a little computer program with a very nice web interface where you tell it, these are the coordinates I want to point to. This is the filter I want to use. This is how long I want to observe for. And then it stores that in the memory of the computers I showed there. And then the computer decides when that source happens to be at the right part of the sky, when it's risen high enough in the sky. And then it sends a signal to the telescope to move over and take the observations. It's pretty amazing to me. So we call it a remote telescope, but it really is a robotic telescope. It really is pretty automated. And so besides all these other great things I'm talking about, why is it here, right? Why Great Basin National Park? And that's because of the sky that we're going to see very, very shortly. And very, very importantly, right, this is an international dark sky park, which means, right, the sky is protected, right? One of the few places in the country where we have protected skies. The closest source of substantial light pollution is Ely, 70 miles away. And so I said this is a relatively small telescope as far as professional astronomy is concerned, but this thing is way more powerful than it should be, because you rarely get to put a telescope like that in a location like this. And we're pretty high elevation, we're like 6,000 or 7,000 feet. Pretty high elevation, we're not looking through that much atmosphere. And overall, we mostly have good weather most nights of the year. So this is a really, really powerful place, and we're getting a lot more bang for our buck by putting it here. And again, we'll appreciate this tonight when we see the sky. But I urge you to go to our website, the greatbasinobservatory.org. You can see some of the pictures of the research that we're doing, but there's also this Preserve the Night Sky, and just lots of stuff about all the outreach and things that the park is doing to help stop light pollution. So I definitely urge you to go visit this website. Okay. Maybe I'll come back to this at the end once it gets a bit darker, but this is the power of having really, really dark skies. This is a former student at the University of Nevada, Reno, Andrew Sundquist. And this is just a little project he did where he took an image of what turns out to be a really, really small dwarf galaxy. I don't know if you can see this little cigar-shaped thing there. This is a tiny galaxy that only contains about 100 million stars in it, which is pretty small. Our galaxy has 100 billion stars in it. For those who are stargazers, this is a 20th magnitude source. Right? Can anyone in the backyard, anyone reach 20th magnitude? Yeah, you need to be here, basically, with that size telescope. We can't do it from Reno with a celestron. And this was like 5 minutes of exposure. So, it's not a crazy amount of time. And so that's what you get with this type of telescope at this type of location. And it's just a really beautiful image. I mean, the telescope performs so well. Besides the stuff I do, I just want to mention also some of the other things that are happening with the telescope. And a lot of this is being done through the Great Basin National Park Foundation and also our partner institutions with the Great Basin Observatory, primarily now Southern Utah University. And they have a program called Reach for the Stars, which does a lot of outreach going into elementary, middle, and high schools. And here you can see lots of pictures of this kind of activities being done. You can see some solar system stuff in the corner. I'm guessing phases of the moon on the left side. And so there's really, really active programs that are being done by the National Park and the National Park Foundation. And it's just, I think, just an incredible group of people, incredible stuff that's happening in the local community. Some of the other stuff, I think, I have to admit, I'm not very well informed on everything the foundation does. I only see the astronomy side of it, but they have a lot of stuff going on. This is just one piece of it. So some of the things they do is organize tonight. The star train that goes from Baker, support astronomy interns at the park and weekly astronomy programming and things like that. And I have to put Aviva O'Neill up here. She's the executive director of the Great Basin National Park Foundation. And she has just been an incredible driver of getting science done with the Great Basin Observatory. I feel like people in her position never get enough credit because she's the person who talks to the rangers and talks to the scientists, talks to the engineers, talks to the philanthropists, and she talks to everybody and just communicates in this beautiful way that lets everyone get their little bit of the job done. So without her, I know I wouldn't be here today having the successes I've had with this particular telescope. And then once you start naming people, you have to name other people. There's too many to name. Lots of people contribute. It really takes a village. But I mentioned Paul Gardner earlier, who was instrumental in getting the telescope up and running. The park rangers have been incredibly helpful and always willing to help when we need something on site. The interns, posting things on Facebook and outreach and helping do educational things. Just many people going into this, and I'm just sharing my small part of what we do with this telescope. Okay, so who uses the observatory? It's mostly students. And so this is one of the few kind of graphs I have in here, but every year there's a survey that every user of the telescope uses. It was put together by this person, Professor Quinton Sedlacek, who, I made a mistake up there. He's at Southern Methodist University in Texas, not Southern Utah. But he's an education researcher. And he's kind of surveyed trying to understand what is the impact of using the Great Basin Observatory in students' education? What are students actually learning from this? And so every student who uses it takes this survey before they start using it, and then they take it after they've done their project, and he measures the growth of what they learn and where they learned. And there's pretty steady growth in all areas. People become more comfortable doing science, right? Which is kind of what we're after. The strongest signal has been there's very clear improvements in students' ability to communicate data, so to make plots and to explain their science to other people. And this is kind of the breakdown. Probably about 40% are college students, and this is mostly what I'm leading here. And then the National Park Foundation and a colleague at Southern Utah University are really engaging a lot of high school and middle school students. And one thing that the survey kind of clarified is that a big chunk of the users are middle school students, and they're doing original science, which I'll show you in a slide or two. This is extremely, extremely rare for middle schoolers to have this type of access to doing original science. And so this is a really, really unique and powerful thing about the Great Basin Observatory. Yeah, Sahan. So the question is, so this can be a longitudinal study. I'm not sure, as far as I know, nothing that would, not an exact longitudinal study, if I can say it that way. This will turn into something of that sort, but it won't be a proper one. I think that would be an excellent next step. Yeah. And are any of the middle schoolers here? Anyone here from White Pine Middle School? There's a school in Ely that's doing a lot of research. But one of the things that I love, and to me this is what it's all about, and sorry for lack of colors here, but this is one of the questions on his survey. The lighter color on the left of the bar is the pre-survey, and the darker colors are the post-survey. And there's 4 different questions here, and as the bar gets higher, that means that the student agreed more strongly with the statement. And the first 2 on the left I'll read out. I think of myself as a science person, and my classmates recognize me as a science person. Both of those statements students agreed relatively strongly with at the beginning, but there's such clear improvement after they did their project with the Great Basin Observatory that they felt more like a scientist. They felt that other people saw them more as a scientist. And to me, this is, we look at the beautiful sky and we're doing science and we're like learning the physics of what's in the cosmos. But to me, this is what it's all about when you're engaging students. Right? We're trying to get people to see that anyone can be a scientist. It's no longer just that old guy in a lab, in a white lab coat, sitting with a microscope, right? Anyone can be a scientist. Anyone should be a scientist, right? And what we need to be doing is building confidence that even if you don't think you're good at it, you probably really are. And we need to show people that they can do it if they want to. And so that's kind of one of the things that drives me to keep using the Great Basin Observatory, because I don't really care if my students become astronomers. I don't care if they go to study the night sky for a living. What I care about is that they've learned something that they can use the scientific method, that they've learned some sort of skill that can then give them confidence to go pursue whatever their passion might happen to be. So that's kind of what we're trying to use this telescope to engage people with. And the fact that we get to do professional research is kind of just some icing on the cake. So here's some of that type of research. This is with high school students from Professor Cameron Pace at Southern Utah University. These are students from the Success Academy in Utah, and he's engaging them in double star research. And so here's a picture from the GBO of 2 stars that could or could not be orbiting each other in a binary system. And he has them go take repeat observations and see if they can see the 2 stars move in a circle around each other. If they do, it's a binary system. If they don't, it's not. They just appear to be a binary, but they're not a real one. And so he has these students following that up. And after they do these projects, they publish their data in the Journal of Double Star Observations. So all these students get to leave high school and put on their college applications that they have a scientific publication. And these are the middle schoolers, the last cohort that he's done this project with at White Pine Middle School. And this is Kaylin Porter's science classes. And here's them, picture of them at the telescope, 2 students using the telescope. And they're doing the same thing. They're using the telescope to look at binary stars. And now middle schoolers, right, are getting a scientific publication. And so the younger and younger that we can, have students doing this type of research, kind of the more just familiar and comfortable you are doing science. And so these are, in my opinion, amazing programs that there's going to be plans to be continuing quite a bit. Any questions at this point? Yeah, way in the back.
As a scientist yourself, scientists are question everything. What's your biggest question?
Well, that's my biggest question. Why are we here? That's a good one. So, I mean, the thing that drives, I'll get a bit specific to what drives me as a researcher in my particular field. But the thing that drives me is, because I study black holes, how did they form? How did they come to be? And one thing that we learned with black holes is that as black holes eat stuff, they emit a lot of light. They put a lot of energy back into the universe. And in order for galaxies and stars to form, somewhere around there's a black hole that could be disrupting a galaxy and star trying to form. So trying to understand how a black hole actually helped control or not control how galaxies might form is something that I'm very, very deeply interested in trying to understand. Which does go back to why are we here, right? How did the universe form, and how did we get stuff that we see today?
How was the universe created?
Sorry?
Big Bang Theory, or was it a creator?
Right. So, well, I mean, I take the scientific approach. So, I'm taught the Big Bang. I'm taught cosmology, and we can take observations of the universe and we can test predictions of the Big Bang. They all hold up. But we don't know what happened more than 10 to the minus 43 seconds before Big Bang's, after the Big Bang started in that theory. And so, there's always room. There's always room. Like Einstein was a deeply religious man, right? I believe that Einstein believed in the creator, but that's not what but that's not something that our scientific method can answer in terms of Big Bang cosmology. Yeah. So yeah, I think what you're probably referring to is some news stories that have been out with the James Webb Space Telescope. And they're seeing, because now we're peering back to as close to the Big Bang as we've ever seen before. And there's predictions of how long after the Big Bang it would have taken galaxies to form to be as big as they are, like our galaxy, for instance. And when they can measure the distance of the galaxy, that tells us how old that galaxy is after the Big Bang. The galaxy is looking much, much bigger than the standard theories might have predicted it would be. And so this is causing problems, or I shouldn't say problems, but this is opening new theories or new ideas for how you can get the galaxy to form so quickly and get so big so quickly. I say the explanation we don't have yet, but this is how the scientific method works, right? You make the new observations and you test those observations against your theories until the theory breaks, you make a revision, and you keep iterating until you get the right thing. So. But yeah, that's been one of the big open questions that the Webb telescope has put out so far. Right, yeah, so it's a very good question. So it's not actually coming from the black hole itself. If this is the black hole and stuff is falling in, there's a place, if the stuff were to get close enough, it would go through the black hole's event horizon, never to come back out. But these X-rays we're seeing are stuff that hasn't gotten to the event horizon yet, so it's still able to escape. Yeah. It's a very good question.
Anything you see that's got you concerned about our future?
Not from space. Yeah. We are, as telescopes are we're getting better at handling data, there's a lot more attention now going into looking for asteroids. And so I'm actually more optimistic about this now, that, because I think that's the big danger, right? If something that did to the dinosaurs does to us. But people are set up now to try to catch that a bit earlier than they ever had before. So I'm actually optimistic in that sense. Cool. I'm going to grab a drink of water. So this is kind of how I have my stuff structured at University of Nevada, Reno. This is how kind of a pyramid where I try to engage students. Most of the stuff we're doing is hands-on learning in the classroom. Every fall, I'm teaching it right now. I have an observational astronomy course where people create projects with the Great Basin Observatory and execute them. Every physics major and astronomy minor in our department needs to do a senior thesis in order to graduate, so they need to do a bit of original research and do some analysis and write a kind of 10, 15-page paper about their project. And then kind of the icing on the cake are the students who have their projects find their way into the professional literature. So I'm going to spend most of the time talking about some of the hands-on learning that we do at Reno. And most of it is done through this observational astronomy class, which I didn't develop. I'll say borrow instead of stole from this person, Professor Melody Rodrigue, who is an amazing professor we have in Reno. She developed this astronomy class, and she was instrumental of getting the Great Basin Observatory, getting University of Nevada, Reno involved in the Great Basin Observatory. Without her, I wouldn't be here talking to you right now. And so this class is project-based. This is Casey Rodrigue, who is our teaching assistant in most years, and he also does a lot of the operation of the Great Basin Observatory. We have about 15 students every year who we teach them observing and data analysis techniques. They develop some sort of hypothesis that they can test with the GBO. Then I have them walk through kind of the steps that professional astronomers would do. They have to write a mock telescope proposal. They basically have to beg for time to get their data with the Great Basin Observatory, which we just give it to them anyways, but they go through that process. We have them review each other's proposals, which is something that happens in the real professional science community. They execute their observations, they do their interpretation, their analysis, and then at the end, they create a poster, which we run like kind of a mock conference at our campus planetarium every year. And so I'm going to show you some of the projects. This is last year's cohort at our planetarium. This is after they did their final presentations. This is basically their final exam. And so we have about 15 students. And one thing I love about this picture is this is their final exam and they're smiling. Right? I'm very proud of that as a professor. And so, for the most part, they really do enjoy this because they've created something that they can take ownership in. And for many of them, it's something that they had never done before. And they become successful at the end. So luckily, the sky is getting darker. We can see these images a bit better. These are images taken with the Great Basin Observatory. This is, I put it up there, never mind. I won't give you the quiz. This is the trapezium cluster in the Orion Nebula, about 1,300 light years away, right? This is the middle star in Orion's belt, in the sword hanging from Orion's belt. So this is a stellar nursery. New stars are being formed here. And if you zoom in, these two students did a project where they could resolve individual clusters of stars being born. These are basically just hot clouds of gas that are collapsing into basically become baby stars. And by looking at the colors of all these stars, they're able to make an estimate that the total mass of these stars is about 2,000 times the mass of our sun. And so this project I thought worked beautifully, and it's kind of amazing to me that these are juniors in college who have prior to this class, they had no research experience whatsoever, especially in astronomy, and they can point to Orion and tell us there's 2,000 stars being formed at that part, right? This is kind of the method that they're learning, and this is basically through the teaching of the scientific method that they can do this. This group on the side, this group went a bit further, and they kind of measured how many stars there are, basically the density of stars, how many stars there are in different parts of here. And then they tried to make a guess of which of these stars might be more or less likely to have planets around them, based off of what the larger environment was. This is one of the first group projects that I had. This is the first time I taught the class in 2019. This is, I think, a really pretty picture of the Crab Nebula. So this was a supernova that went off 1,000 years ago, about 6,500 light years away. And this idea of not necessarily training new astronomers, but training just new scientists, people to go out and use some of the stuff they learned in this class and put it into the real world. This group, I think, is an amazing example of that. My mic just went out. All right, can you still hear me? Yeah, okay. So Sarah Colangelo was one of the students who worked on this. She's now a elementary school teacher in Reno. Last I heard, Katie Cuddleston is studying psychology in graduate school. And Jacob Tresca is University of Arizona studying optics in graduate school. Right, so these are people who used astronomy to help them in their training to get to their future career goals, right? And so this is something that I'm very proud of, is that people are going off and using these skills to learn other things. This is another project done by a student who's now a software engineer, and another student who was a graduate student in physics and now has gone off to do, I think, some like satellite stuff. But these are two galaxies 200 million light years away that are merging with each other. They're two galaxies on a collision course. And you can see a zoom in here, these kind of two cigar shapes. And these students kind of measured what the profile of these galaxies are, and showed that that this galaxy here can feel the gravity of that galaxy, and vice versa. Another example, I talked about kind of chasing supernova, chasing transients earlier. Yeah. Oh, yes, absolutely. Thank you. All right, is that better? Mm-hmm. Thank you, Bradley. So this is a group that kind of monitor these things that we call astronomer telegrams, which are exactly what they sound like. That when something exciting in the universe happens, people put out a telegram. We still call it a telegram, but it just goes to a web page now. It announces, at this coordinate in the sky, at this time, we discovered a new star that wasn't there before. So this group was following these telegrams and found a group that announced the discovery of a new supernova that went off, I'd guess probably 2 days before this, so like October 15th, 16th, 2020. This is the picture of the Great Basin Observatory. You can see the star right there. Here's the same field 1 month later, and you can see it's basically hardly there. Can't even visualize it. So this was the supernova. It was really bright. A massive star exploded, got really bright. Then over the next month, it faded away and became dimmer.
Is that in this galaxy?
Yeah, that's in this galaxy. Yep. Oh, no, I'm sorry. No, not this galaxy. Sorry. This one, actually, I didn't put the distance there. Oh, distance unknown. But yeah, this would have been, this could have been billions of light years away for all I know. I showed kind of their first and last image, but they wound up taking about a dozen images over the course of that month. And so here's a figure of how bright the star was versus time. So every day goes from 0 to 30 days, or about a month. And you saw over time, I kind of just drew this to guide your eye. It got fainter, it kind of flattened out a little bit, and then it dropped really fast. And so through this, they could actually determine that this was a massive star that went supernova. Because there's two types of ways to get a supernova. One, you have a very, very massive star that runs out of fuel in its core and it just winds up exploding, leaving behind either a neutron star or a black hole. The other way is you could have something we call a white dwarf, which is kind of what our sun will turn into in about 5 billion years, as it sheds its outer layers, it leaves behind its bare core, which has about the mass of the sun crammed into something the size of the Earth. And if you could somehow keep adding mass to that kind of white dwarf, it would eventually explode and also goes to supernova. And when a massive star explodes, it shows this characteristic shape that my students found, while if a white dwarf explodes, it shows this characteristic shape in terms of how its brightness changes with time. And so through that, again, it still amazes me, right? This telescope that's just, a few miles away from us right now could determine that somewhere billions of light years away, a star ended its life, and it could classify that it was this type of star, not the other type of star. And finally, this is one of my favorites. I had a group last year that tried to determine what the light pollution is in Reno compared to here. So this is a picture of the same exact part of the sky. They're a little bit offset. This star there is the same as that star. This was a picture taken with a celestron on the top of our physics building in Reno. And this was the same star taken with the Great Basin National Park, with the GBL, the Great Basin Observatory, taken on the same night. And it's kind of scaled to take into account the fact that the celestron in Reno is a slightly different size than the Great Basin Observatory. But you can just see the background, how much harder it is to see stars in the picture from Reno Versus here, you see all these little points of light there. These are all stars that are just being swamped out by the city light in Reno. Here's kind of a satellite view of there's Reno, there's all the light pollution, there's Ely, and there's us, where we are right now. Okay, so moving on from some of the kind of hands-on learning in the classroom that we did, and on to some of the more kind of getting closer to professional research. This is a former master's student from the University of Reno. He's now taken his astronomy background and he's working for the city of Reno as an engineer. This is his result, which was he was monitoring a star, and I'll show you a graphic of the star in a bit. And here's how bright it is versus time. He watched it for about 200 days. So he basically watched this star every night for 2/3 of the year. He saw, at the very beginning, he saw this dip. It was very, very dim, and then it kind of went up to a steady level. This is a famous star that's called Tabby star that he decided he wanted to monitor. He wanted to join in on what other people were doing. And this was a star that had been discovered to show these really, really strong dips, this kind of thing that you see over on the left side. And no one understood why, right? This is one of these things you see a question, you have no idea what's happening, but over time, the scientific method works out. But at the very beginning, for Tabby's star, they're like, well, we've never seen any other star display this behavior. It must be aliens. We discovered an alien civilization that has constructed a megastructure around their star, and that megastructure stole all the light for a short amount of time, and then it let it get through again. Obviously, that's not what happened, but over time, what people realized is that here's a kind of a graphic of what might be happening, is that this star, this is a picture of maybe comets going in. The latest I've heard is they think maybe a planet orbiting the star has a moon around it, and that moon wound up falling into the star. And as the moon fell into the star, the moon kind of got ripped apart and put a bunch of like dust and just kind of debris around. And some of that debris would have blocked the light coming from the star from a short amount of time. And then as that debris passed around the star, we get a nice view of it again. So his thesis was kind of just contributing to a bit more data to try to understand some of these dips that this unusual star was showing. And I'm going to spend the rest of the time talking about one of my former students, Alexis Tudor, because she is, in my opinion, the shining example of someone who basically walked up the entire pyramid. She started in the classroom, went on to do a senior thesis, and then went on to do a master's thesis at the University of Nevada, Reno, all with the Great Basin Observatory. And she is a spectacular student. She won a scholarship that the Great Basin National Park Foundation puts out every year for given to one student for using Great Basin Observatory every year. And she was also the winner for the Outstanding Graduate Researcher across all of the University of Nevada, Reno for her graduation year. She's now working for L3Harris, doing writing software for satellites. So I'm just going to kind of briefly walk through some of the stuff she did. She started in my observing class, and she knew immediately she wanted to study something called cataclysmic variables, which was amazing to me because who here has ever heard the word cataclysmic variable? Yeah, I hadn't until I was like midway through graduate school, if that. It's not something most people but she came in with this dead set. She had just read something about it, and she just wanted to work on it. And lo and behold, she got really lucky that she was following these astronomer telegrams too, and someone discovered one during the class, and she threw GBO on it. And what a cataclysmic variable is a white dwarf. So this is the remnant of something like our sun, the bare core after what our sun will look like in 5 billion years. And if it's in a binary system, material from the other star could fall onto the white dwarf, form that same kind of disk that I showed for the black hole picture. And then as material falls onto the surface of the white dwarf, eventually it kind of builds up, and you get a little like nuclear explosion on the surface of the white dwarf. And it gets really bright for like maybe a week or two. So someone announced one. Again, this is not a real picture. This is just an illustration. But this is a real picture with the Great Basin Observatory. She just kind of gave it this color scale that makes it look a bit green. But this is a real picture with the GBO. And with her group, she found this star right in the middle, and there's your cataclysmic variable that was going through a little bit of an outburst. And so she took, I think, 6 observations with the GBO, and here's how it changed its brightness with time. And this is a very characteristic shape for one of these cataclysmic variables. And again, what you're seeing here, and again, it astounds my mind that this little telescope in the in the middle of Nevada is observing a nuclear explosion happening from outer space. The distance to this I don't know, but it's probably about 1 billion light years away, is my guess. So that was what she did in the classroom. She went on to do a senior thesis on a very similar type of object. Something we'd love to put weird, jargony names to things, but these we call intermediate polars. It doesn't really matter what it's called. But again, you have a white dwarf here. It's the same idea that some material from another star is falling onto the white dwarf. But this white dwarf happens to have a really, really strong magnetic field. And that magnetic field kind of like stops material from falling directly onto the white dwarf. And it just kind of pushes away and clears out the inner part of this disk. She did a project advised with one of my former postdocs, Dr. Aaron Shaw, who's now a professor at Butler University. And this was a pretty heavy-duty project with the Great Basin Observatory. Aaron and Alexis observed a different source. This is a real image with the Great Basin Observatory, but this is a different source from the previous one. But right there, they observed it every night for about a month and a half. And then you see how the brightness changed. And it turns out it didn't actually do anything very interesting. It just kind of stayed steady. But what they're hoping to see is that every once in a while, these sources suddenly dip and then get bright again. And they're hoping the GBO would happen to catch that. In this particular case, it did not. But what this did was set the foundation for what turned into Alexis's master's thesis and what turned into the professional research with the Great Basin Observatory. And so after she did that, she went on to do a master's in computer science, not astronomy, not physics. And this was her advising team, me, Aaron, and then a professor in the computer science department, Sergio Descalu at University of Reno. And his specialty, what became Alexis' specialty, is what's called human-computer interactions. And this is just anything that a person interacting with a computer, right? This is the science of how is that person going to interact? Things like how big should Google make their text box when you type a search so you don't miss it, right? That type of thing. There's actually a lot of research that goes into trying to figure out the optimal way to do that type of thing. And so that's what she's really interested in. And the work I'm about to show, it led into her giving a couple conference presentations, and she had a published paper in a journal called Astronomy and Computing, which is like the perfect match of her interests. I don't want you to read this or anything. I'm just trying to brag how smart Alexis is. This would look really confusing and complicated, and it is, because this is something that she really spearheaded. But the idea is that she wanted to build a piece of software that would be very easy, very intuitive to use to automatically reduce data from the Great Basin Observatory. So she did a bunch of user studies. She did a bunch of designs, and she basically asked people, if I make a piece of software, would this be an easy thing for you to use or not use? And so she did a lot of surveys and analysis on the results of those surveys to try to figure out what's the best way to make this piece of software. But she found that she could give someone who doesn't know anything about astronomy, never heard of the GBO before, she could give them her software, and they could reduce the data in average in about 10 minutes. Which I think is pretty impressive. I'm currently using this in my observational class to teach new generations of students how to reduce data. And it was designed for the Great Basin Observatory, but it can be used in any telescope. It's very, very portable, very flexible stuff.
What's data reduction? What does it
Yeah, so data reduction means when you take the raw image. So it's basically turning this picture into this on the right. So it's basically, it's measuring how bright a star is in a field. Yeah, so that's what she wrote a program in order to do that for us. This is the product that she made. And so basically you open up a program on a computer, and it just gives you this nice like graphical interface. And there's help files and everything where you put a whole bunch of parameters in here. So, but these things are basically like you click on a button here, and it pops up a window that has you then browse to find the file on your computer, right? Things that many of us have done a lot of times on computers. And then there's just some questions about what are you looking for your data, what type of brightness are you trying to measure and stuff like that. And you just answer a bunch of questions, and then it displays the data for you, and then you get out a nice plot like this. And so some of the stuff that we showed in that in her paper, and some of the research that we're doing here, is how a professional would look at images of a black hole. So every point here represents how bright a particular black hole in our galaxy is as a function of time. And you see that the light is getting brighter and fainter, brighter and fainter. And her software is able to show that this brightness and faintness is not just random. It's actually larger than you would expect it to be by just random chance, which is an indication that there's something like a black hole there. I won't get too much into details. This one I think is really cool. This is the data that my 6-year-old was taking on one of the very first slides here. This is what she was observing. This is a white dwarf that's spinning, and as it spins, from our point of view, there's a hot spot on the surface of the white dwarf, and as it spins, the hot spot sweeps in our line of sight and away from it. And so as it spins, it gets brighter, fainter, brighter, fainter, and you see this kind of like oscillation like that. And so the telescope showed that this white dwarf is spinning every 20 minutes in its one revolution. Do I see a hand or?
Looking at the ISS.
Oh, nice. The space station? Oh, that. Is that the space station? Cool. That's a good distraction. Okay, so this is another example of a white dwarf that was doing nothing, and this one actually showed one of those dips that Alexis was trying to find earlier. And I just want to highlight, this was done by another student at the University of Reno. It was for Alexis's thesis using her software, but the program was run by this student, Ava Covington, who was also another winner of the scholarship that the Great Basin National Park puts out. And she also won an award last year, awarded to one student across the entire University of Nevada, Reno. And some of the reasons she won that award was for some of the work that she did with the Great Basin Observatory. So again, just this idea that we're trying to use this telescope to just kind of give scientific literacy and just try to give students experiences and confidence that they can become scientists if that's what they want to do. And finally, this is someone else who applied Alexis's software to basically make a whole bunch of other data reductions of other sorts of white dwarfs, and he found a whole bunch of dips. Each one of these data points represents one native observation of the same source in the Great Basin Observatory, scattered over about a year and a half. And there's about a dozen different objects that we made similar plots for. And this person used the GBO. He's now writing software for video games. Right? So we're doing very, very different types of things with this training. Okay, and that brings me to my final slide, is that, right, this is just, for me, this is the beginning. I started in Reno 5 years ago, And so I'm just kind of getting the system going from my end and just kind of getting my feet wet and understanding what I can do with this telescope. And so the plan is to just keep continuing, keep building on what we've already done. And here's the current cohort of my current students in my observing class, and they're about to start their projects in about a month or so. And so we'll see where they go. And so, yeah, thank you for your time. And happy to take some questions. I'm going to be hanging around for a couple hours, I imagine, so feel free to come find me as well.
Are the images you're getting from the GBO, are you receiving them analog or digital?
They're digital. Yeah. It's a CCD camera.
And so that's how you can get the data.
Yeah, exactly. Yeah.
So you were talking about the Tabby star,
Mhm.
or the observator. Well, first, can you comment on Betelgeuse, and then second is, has GBO been observing Betelgeuse in the past?
Yeah, so Betelgeuse was doing weird stuff a couple years ago. It was getting really bright and no one really knew why. As far as I know, they thought it might be a precursor of Betelgeuse going supernova in the near future. And I think we're still in a holding pattern on that, as far as I know. I don't know if anyone actually pointed GBO at it. I think we talked about it, but it's almost a little too bright for the GBO to get really high quality. It would saturate most images for the GBO. I can't see it all, so if you have questions, just shout it out.
GBO use the visible light spectrum?
Yeah. Yeah, optical light, so the same thing our eyes see. All right, well, thank you again for letting me come and talk to you, and yeah, enjoy the sky.